It's all of electrochemical shows PMT, electrochemical cells PMT sheet, yeah. It's pertinent then, yeah. So question 1A, state the meaning of electrochemical series, yeah. So obviously, this over here is an electrochemical series. You got the electrode potentials of each reaction going in a numerical order, yeah, from least to highest here. So what you need to write here is just simply a series of electrode potentials in a numerical order, yeah, that's it. A series of electrode potentials in a numerical order. Alright, let's move on to the next one. We've got part B, yeah. State two conditions that are needed for the following half cell to have E of 0, 0. So that's a standard hydrogen electrode, yeah. So you should know that the conditions for the standard hydrogen electrode, yeah. If you don't know this, it will repeat bare times, so you'll get to know. There's temperature of 298 Kelvin, hydrogen concentration of 1 mole dm cube, yeah, and hydrogen gas at 1000 kPa. So those are the three conditions. Yeah, I don't think you need to write all three to get the mark here, but it's minor. Just one of those here will suffice. Obviously, we've got H2 here, gas, so they will like that one there. And you get me. I identify the weakest reducing agent on the table, yeah? So as you see, yeah, all of them are moving, all the things on the left-hand side are accepting electrons, yeah? So that means that they are being reduced, yeah? A reducing agent, yeah, gets, obviously fucking, it gets oxidized itself, yeah? And it reduces other things, yeah? So therefore, we're going to be looking at the right-hand side here, because these are things that are going to oxidize back into the left-hand side. You get it? So the right-hand side, if we look at this bottom thing here, that's a 1.8. That's a very high electrical potential. That's the highest one here. So that means that this forward reaction here is extremely strong, yeah? This CO3 plus is accepting electrons, is being reduced very quickly into that. So what's the likelihood of this oxidizing back into this? Is very unlikely. So that makes this the weakest reducing agent, yeah? Alright, calm. So the weakest reducing agent is this cobalt complex thing here. H2O 6 2 plus, yeah? Alright, safe. Next question, yeah? D. Use half equation from the table above to deduce an equation for the reduction of vanadium, whatever, into iron, by iron, yeah? So you're going to need to use two equations. So you're going to need to use the vanadium one, yeah? So the vanadium is over here. So just copy that out, basically. Let me give it a little bit of room there. So vanadium here is, the vanadium equation here was VO2 plus 2H2O plus 2H plus, sorry, yeah, plus E minus goes to VO2 plus, yes, this is just copying it from the table, yeah, plus H2O, yeah. And now we're going from, it's gonna be by iron, yeah. So hence we need to look at the iron thing here. So it's by Fe iron going that way, yeah. Now, the way I know that's going left, this iron one, is because this has electric potential of minus 0.44, and minus 0.44 is smaller than 1.8. So it's always the bigger one that's gonna go forward. So therefore, so not 1.8, 1, yeah. So it's gonna go forward for the vanadium, and it's gonna go backwards for the iron, yeah, because that's smaller, yeah. So that's gonna go to the left, yeah. Calm. So just write that to the left, basically. So write it out, but to the left. So write Fe plus 6H2O goes to FeH2O6, the complex ion, 3 plus, plus, sorry, 2 plus, plus 2E minus here. Calm. And now what you gotta remember as well is we obviously have another ion equation which is down here. So this one's a bit techie here. What's going to happen basically is after you form FeH2O6 2 plus here, because this is also smaller value than 1, yeah, it's going to do this reaction as well. So it's going to go from FeH2O6 backwards to FeH2O6 3 plus, yeah. So after you form this, it's going to turn into Fe3 plus, yeah. So you need to account for that as well. And because we had 2 electrons given off here, and 1 electron given off here, it's going to be 3 electrons in total now. And the final product you're going to produce is 3 plus. So all you need to do here is just tweak this equation here to 3. And instead of 2 there, 3. That's it. And that will pattern it, yeah? So that's your two half equations there, yeah? So now you just need to combine them. So obviously, because this down here is 3, and that up there is 1, you need to times the top equation by 3. So that becomes 3VO2 plus here. This becomes 6H plus. This becomes 3E minus there. This becomes 3 there, and this becomes 3 here, yeah? Alright, calm. And then just combine it. So when you combine half equations here, obviously you add the two, and the plus there. So obviously you add the two, yeah? So you put all the reactants together. So 3VO2 plus Fe from the bottom plus 6H plus from the top. And then this 6H2O, yeah, you've got 3H2O on the right hand side. So when you have a the same thing on the right hand side, sorry, same thing in the products, yeah, same thing in the reactant, yeah, you see which one is bigger. Here the reactant one has more. It has 6H2O. The product side only has 3H2O, yeah. So therefore it's gonna you need to take away this 3 from the 6, always bigger number minus smaller number, and that's gonna go to whichever side had the most. So reactants had the most, so we're gonna put 3H2O there, yeah. Alright, cool. And then you're making electrons are going to cancel, 3 on the reactants, 3 on the products going to cancel out, and you're going to be making this Fe bullshit over here. And then obviously also the product from up here, so 3VO2 plus here. If you have any problems with that, then go see the other video as well, redox video. It has a lot of half equations there of how to do it properly. So yeah, that's how you combine half equations, yeah. I think in the electrochemical video, the content, yeah, I said something about some like anti-clockwise arrows and that, yeah. That can also work. It's calm. You can do that method as well. It'll work. Just remember that the Fe3 plus here, you're making Fe3 plus and 3E minus, yeah, not Fe2 plus and 2E minus, yeah. That's the only difference. Just because of the way this question is. Alright, come on. Question E, yeah. Use the data from the table to explain why cobalt will undergo a redox reaction with Fe. Okay, calm. Well, let's look at. So whenever they ask about will it undergo reaction or reaction, whenever they mention that bullshit, yeah, it means that basically what they want you to do, yeah, is to say that something has a higher electrode potential than another thing, basically. That's how it always is. So we're looking at cobalt and we're looking at something else. We're looking at cobalt here, hello? Yeah, and we're looking at iron, innit? So iron H2O bullshit here. Yeah, we're looking at this one and this one, yeah, because we're talking about 2 plus going to 3 plus, yeah. So obviously, as you see, this one has a smaller electrical potential, yeah, compared to the cobalt one, yeah. So therefore, it's going to be going left, and the cobalt is going to be going right. And as a result, obviously, cobalt's going to be reduced, iron man's going to be oxidized, and that's the situation that you've got going there. Yeah, so that's why they're going to react, because that one is smaller than that one. That's why it's going to react. So therefore, yeah, explanation. Fe3 plus, yeah. And so because the cobalt one is going forward and the Fe3 plus one is going backwards, that's why I said Fe3 plus and not Fe2 plus here. The equation is going to be very simple. As you see, they both have one electron. So one electron there, one electron there. So electrons are just going to cancel. There's no need to balance anything here, bro. So all you need to do is just write this reactant here. This is going to be the reactant on that side, and then product and product. That's it. So it's simple, yeah. So just basically CO H2O6 3 plus open bracket Fe H2O6 2 plus. It's going to produce. So that's the cobalt reaction going forward. It's going to produce CO H2O6 2 plus, and then cobalt reaction going backwards is going to iron reaction going backwards is going to produce Fe3 plus here. So Fe H2O6 3 plus here. Alright, come on. See. That's the equation there, yeah. So just why two cobalt complex ions on the table have different electrode potentials here. So if we look at the two ones here, we got this one that's attached to water, and we got this one that's attached to ammonia, yeah. So the one with ammonia and the one with water, what we call these little things here, you might not have taken it yet, yeah. You'll take it in transition metals, yeah. It's called ligand, yeah. So these two are different ligands. Ligands when you got like a complex, like a metal complex ion, yeah, that's attached to like waters on each side or something, yeah. So here you got 6 waters, yeah. So you can imagine that's how it looks. Another one has ammonia. So obviously, different ligands, it's going to be different electron potential here. So hence you can write here There are different ligands, yeah. Alright, calm. Let's move on. Question two or three or whatever. Question two. Alright. Use the data on the table above to explain why aqueous electrolyte is not used for lithium cell, yeah? So obviously if something's aqueous, yeah, that means that it's going to be containing water, yeah? So if it's containing water, yeah, let's look at the water. Again, they're talking about reactions here, so something to do with electrical potentials, yeah? So let's look at water, yeah? So water has electrical potential of minus 0.83. Lithium has one of minus 3.04, yeah? That means that lithium is smaller, yeah? So hence what we can write here is that, I'll write over here. So what's going to happen is lithium is just going to react with the water and then it can't react with the iodide in it. So that's the whole point, yeah? That's why this is not going to work here. So obviously the reason for that is obviously, yeah, this one's smaller, so therefore the reaction is going to go like that. Li is going to release an electron here, and then this one's going to go like that. It's going to go forward because the number is bigger. So as a result, yeah, this is going to accept electrons, yeah, it's going to be reduced, and this one's going to be oxidized, and it's going to do redox here. So obviously you don't want that to happen. Otherwise, it's not going to do it with the I, which is what you want. Alright, some bullshit here. Use the data in the table above to calculate the cell EMF of a standard lithium iodide cell. Yeah, so standard cell EMF. Yeah, pretty patterned. Yeah, pretty simple here. We're looking at iodide and lithium. So lithium is minus 3.04. Iodide is plus 0.54. So EMF is just gonna be the bigger one minus the smaller one. So it's just the one that's reduced minus the one that's oxidized. So that minus 3.04. Yeah, and that's gonna get you 3.58 volts here. So that's the final answer there. An EMF value for commercial lithium, whatever, is 2.8. Yeah. So you're asking why is that different to, why is that obviously not 3.58? Yeah. Well, obviously, this is actually a very common question. Yeah. If they ever ask you why is EMF different from the other one was a standard one, bro. It was a standard lithium iodide cell, which means it's under standard conditions like the 298 Pascal, like Kelvin and all that. Yeah. So hence what you should go right here, yeah, is you even say there are different conditions, yeah, or you can just memorize non-standard conditions. If you write non-standard conditions, you'll get the mark. You get me? My man decided to just fuck off. Alright, calm. Let's see the situation then. In some lithium cells, lithium, whatever, is used as an electrolyte. Deduce the oxidation state of chlorine in that, so it's pretty simple. Yeah, if you watch the redox one. If not, then you need to learn. So obviously, oxygen is always -2. Lithium always has to be +1. The only one that's a variable is chlorine. That's why they're telling you to deduce oxidation state of chlorine. So if that's -2 times 4, that's -8. I've got +1 needs to balance to make 0. So chlorine has to be +7 here. Yeah? That way it's +7 plus 1 is +8. -2 times 4 -8. It balances, yeah? Alright, calm. In other lithium cells, lithium cobalt oxide electrodes and lithium electrodes are used here. Given the equation for the reaction that occurs at the positive lithium cobalt oxide electron. Alright, calm. So obviously at the positive lithium, so obviously in basically saying in the positive one, you've got a lithium electrode here, so it's going to be positive lithium electrode, so that's going to be the Li plus here, that's reacting there. And obviously you've got it reacting with cobalt oxide. So cobalt oxide looks like that. Make the last O a bit bigger to show that's cobalt oxide. And then obviously that's just going to combine to make LiCOO2. So you're just going to combine together, yeah? Let's see, make that a bit bigger there. So CO2. Obviously, on the left hand side, you've got a +1 charge. Right hand side, you've got no charge. So you just need to add an electron here to balance out the charge here. So that makes sense here. Positive is always going to attach the electron. So therefore, it's going to be, yeah, it's going to make that. You can also write this, by the way, to show that it's, you can write the product if you want. Yeah, they also accept this to show that it's like a ionic compound thing. Like it's an ionic complex here, not just like that. You can show that the actual ionic in it. You can show that lithium is Li plus here, and COO2 is the minus part here. I give an equation for the reaction that occurs at the negative lithium electrode here. So this is pretty simple. To make this Li plus, obviously, it's just Li at the -1. That's obviously going to be making Li plus. It's going to be oxidized to Li plus plus E minus here. like red cat and anox here. Alright, calm. Question 3a. Deduce the half equation for the reaction at the negative one, yeah? So at the negative one, it literally tells you that glucose reacts with water to form carbon dioxide and hydrogen, yeah? So you write that out then, because it literally tells you the situation. So C6H12 here, O6, that's glucose here, plus H2O is going to produce CO2, and that says H plus hydrogen ions, yeah? Calm, fam. So obviously, this is the negative electrons here. So electrons are lost here, because it's negative or whatever. So therefore, it makes sense. It makes sense. Therefore, electrons are going to be on the right hand side. So it's going to lose electrons there. So you're going to lose electrons there. It's going to be on the right hand side. So you need to add that. Also makes sense because you're balancing the charge. And now you just need to balance the equation. It's pretty simple, yeah. Not too much to do here, fam. You got C6 on the right hand side, so you need to add a 6 here. Now you got 12 oxygens to deal with. You can't alter, you can't change this one here. So you got to alter this one, H2O. You got to add another 6 there. So that balances O. And now you got 12H and you got 12H here, so I need to add 24 to balance that. And if I've got 24H plus, I need to add 24E minus to balance out the charge, yeah? So that's the final equation there. Alright, deduce the half equation at the positive electrode, yeah? Calm. The positive electrode is saying that oxygen gas reacts with hydrogen ions to form water at the positive one, yeah? So we just add O2, yeah, plus H plus is going to be making H2O, yeah? That's what it's saying. It's saying oxygen is going to react with H plus here, hydrogen ions to form whatever the fuck here, H2O. Alright, so what do you do now? You just got to balance shit in it. So O2, I've got one O there, so add a 2 there. And then obviously I've got 4H now, so add another 4 there. So now I've got 4H here. That's balanced there. Now obviously I need to balance charge. The final equation is going to be O2 plus 4H plus 4E minus gives you 2H2O, yeah? So that's the other half equation there. Part C, I need to combine the half equations. So write out each half equation separately. So write the first one was C6H12O6 plus 6H2O. Gonna make 6CO2 plus 24H plus 24E minus, yeah? So that's just writing out the first half equation, yeah? So that's that one there. And now the second half equation we had was this thing over here, so O2 plus 4H plus. How many H2Os? Two, hello? Yeah, two. Alright, calm. Now obviously, as you see, you need to balance the electrons, so we've got 24 electrons here, we've only got 4 here, so you need to times the bottom equation by 6. So we've got 6O2 now, we've got 24H plus now, you've got 24E minus now, and now you've got 6H2O, yeah? Sorry, 12H2O, yeah? Times the bottom by 6, yeah? And now obviously combine them, so add them together, so electrons are going to cancel, H plus also going to cancel. So now what you're left with is you're left with the reactant here, so C6H12O6. You're left with the reactant on the bottom, 6O2. The right hand side has more waters than the left hand side. This has 12, this has 6, so it's going to be 6 to the right, because 12 minus 6 is 6. So we're going to produce the product up here, 6CO2. And then we're going to also produce this final 6H2O, yeah? Alright, so that's the final ionic equation for part C. Alright, come on. The negative electrode is made of carbon and the positive electrode is made of platinum. Give the conventional representation for whatever. So we got so it tells us here that the electrode on, so it's always ROR, yeah? So reduced, oxidized, oxidized, reduced, yeah? So it's pretty simple, not too bad, yeah? We got fucking carbon on the left hand side here. Let me write it down here. So we've got carbon on the left hand side. That's the electrode, so that's solid, yeah? Then you got the glucose, which is being oxidized or whatever, reduced, sorry, whatever the fuck, yeah. So obviously you've got that there. Obviously you're gonna show a difference in phase because the glucose is obviously aqueous here. It's a solution here. So C6H12 or 6, that's obviously aqueous here. And now the H plus solution that's also in there, that's oxidized reduced, is gonna be H plus here. And that's also gonna be aqueous here. So you can just tell this from this equation above here. So 6H2O plus whatever. You also had the 24H plus here going there. Here. Come on. And then finally you're gonna have the CO2 that was there in the original equation. And so that's obviously a gas. So therefore you're gonna have to do another phase difference here. And then you gotta do two lines to represent salt bridges. So now salt bridge, now you're looking at the other side. So think about it, yeah. The oxygen is the one that this O6 here is the one that's gonna change into O2. So that's why you gotta write the O2 gas there. And then obviously phase difference, because that's gas. You're gonna put the H plus here, that's AQ. And then obviously because it's still because we're producing water, yeah, you can still write just water here, H2O. And you don't have to write you can put a comma because they're kinda in the same phase. They don't really matter between aqueous and water as long as it's water. You don't have to put a dash line because they're in the same state kind of, yeah. And then obviously the electrode here, which it says was platinum, yes, that's solid, so that's another phase line, yes. So that's the final thing there. Obviously you don't need to write some of the other ones because the oxidation state's not changing. As you see here, H plus going to H plus, so it's not really changing there. CO2 obviously is the carbon is changing onto the right hand side, so that's why we change the oxidation state. It's the oxygen that's changing there in oxidation state. So as you see, carbon goes from C to being to being over here O2, yeah. So that's the difference oxidation states there. So that's why we have written it like that, yeah. Alright, come on. State what must be done to maintain the EMF of this fuel cell when in use here. So obviously when it's in use here, you're gonna need to keep the concentrations constant, yeah. To keep the two concentration, you need to keep the concentration constant, yeah. But you can do that by adding more mass here. If mass is being used up, concentration is gonna decrease. You need to add more of the reactant or whatever, yeah, to keep the concentration constant, yeah. Alright, come. Question 4. Say the subsequent conditions needed in a standard hydrogen electrode, yeah. So this is simple, yeah. Obviously, we need H2 gas. That's the substance here. It needs to be at 1000 kilopascal. kPa, yeah, not pKa. Calm. You're obviously going to need H plus here. H plus, and it's going to need to be 1 mole per dm cubed. That's the other condition there. That's the other, yeah. That's the substance in the condition. Then finally, you're going to need platinum electrode as well. So PT electrode, and you can state the temperature for it as well. The electrode has to be obviously at 298 Kelvin, yeah. Or the reaction in general, the concentration. Alright, calm. Alright, part B. Part B is saying it is difficult to ensure consistency with the setup of a standard hydrogen electrode. A Cu2 plus whatever, bro, there's too much water for him, man. Alright, calm. Your answer should include details of how to prepare the solution of acidified TiO2 plus, yeah? So how do we prepare the acidified thing, yeah? Okay, calm. Let's find out how much mass we need to add of the thing first, yeah? So to do that, yeah, we can write that N is equal to CV, yeah? Moles is equal to concentration times volume. Now you need to find the concentration, yeah? So always when you're doing this standard whatever, yeah, it should always be 1 mole. That's what we said earlier, 1 mole of H plus ions, yeah? And so here we've got, that means that's going to be 1 mole as well of TiO2 plus, yeah? But how do we know that exactly? Let's be sure. Obviously, we've got 0.5 mole dm of sulfuric acid, and sulfuric acid is diprotic, yeah? So it's got H2SO4. So 2 times 0.5 is obviously 1. So we do have 1 mole of that, which means you have 1 mole of this. And so hence we can write that concentration is 1 mole per dm cubed. And how much volume do you have? You're adding it to make 50 centimeter cube of solution, yeah? So you've got 50 centimeter cube. So N equals CV. So that's just going to be 1 concentration times 50 divided by 1,000 to get decimeter. That's 50 over 1,000. We're going to get 0.005 moles. That means you've got 0.005 moles of this TI. That's so for bullshit. And now, obviously, mass is equal to N times MR, yeah? If mass is equal to N times MR, that means it's going to be moles, which is 0.05. That's what we just found. It's not 0.05, yeah? Calm. 0.05 moles times the MR, which it gives you in the question, is 159.9, yeah? That's going to give you a mass of 7.995 grams, yeah? Calm. So that's in the question over here. It gives you the MR, yeah? Alright, safe. So now what you're gonna do here, you're gonna have to describe how you're gonna set it up in here. So place weighing volt on the balance here. So whenever you do this sort of stuff here, always gonna be dissolve it in a very small amount of acid here. So dissolve it in a minimal amount of acid here. Right sulfuric as well. That's what we're using. Remember, it's the volumetric flask here. That is like that big amount of liquid, like where you make it up here, and that's where it's gonna be made up to 50 centimeter cubed here. Alright, calm. So that's what you need to write there. It asks for liquid diagram as well. Show how to connect the electrodes. So to connect the electrodes, you need to just show the situation. So obviously you got the titanium electrode there, so that's TiS solid. You got the shit that's submerged in it. You got the TiO2 plus ions solution, aqueous ions here. That's down there. That's AQ. And then you got the voltmeter, obviously that's connecting it. So put V over here and put that into the second part there. So that's that thing there. Obviously that's gonna be the Cu, the copper, which is on the other side. If you read the question here, it says the copper electrode there. Obviously that's an aqueous solution of Cu2 plus ions here. And then finally, the only thing missing now is the salt bridge. So just do a little line like that, and then write salt bridge. Alright, calm. So that's the diagram, that's sufficient. Let's look at what else they want here. So measurements taken here. So it should include details of measurements taken here. So what measurements are we taking here? Well, obviously we're taking the we're gonna have to record the voltage of the cell. That's the whole fucking point in this shit, innit? Is to obviously find the voltage of the cell here. So record the voltage of the cell. By the way, what we're trying to do here, apparently, according to the experiment here, is find the voltage of one of these here, whichever electrode, we'll find out in a minute. Record the voltage of the cell here, and then obviously, copper is being reduced here, and titanium is being oxidized. Always the one on the left that's oxidized, always the one here reduced. That's just how shit goes, and we can tell that from here as well. Copper, the one here is 0.34. Yeah. So hence, record the voltage of the cell. Yes, the voltage of the cell. Also know from all of this shit, man. You understand? Because it's at the, it says that it's at the, it says which one is at the positive one, which one is at the negative one, or whatever. It says some bullshit. Alright, calm. Let's continue then here. So record the voltage of the cell here. So record the voltage of the cell. So yeah, do that. And obviously E of the cell here is going to be E of copper minus E of titanium. That's going to be forward, that's going to be backward here. So E of thing minus E of titanium here. And so basically we can do that accordingly. We know that the cell is in calm. So we know the standard electrode potential for titanium is minus 0.88, and we know that the one for the electrode for that is 0. Is the cell is 0.34, yeah. Yeah. So the cell is 0.34, and the other one is the negative one, yeah. That means that we can write 0.34 minus 0.88 is equal to 1.22 volts, yeah. So that's what we can find there. So you do the one for copper, take away the one for titanium, that's going to give you the cell voltage, yeah? So the cell voltage is 1.22. And by the way, that's how I knew that copper is on the left and titanium is on the right, obviously. It's because copper has a greater one, whereas titanium's one was minus 0.88, so small, yeah? So do bigger one minus smaller one, you get 1.22. That's gonna be the voltage that you're gonna measure. So how this works here is you don't actually know that here, yeah? So you're kind of working backwards. So what's going on is basically what I'm saying is that when the brother finds the voltage of the cell, it should match up to be 1.22. And since he knows that, that means that he can therefore find the um the E of titanium, which is what he's trying to find. He doesn't know that it's minus 0.88. That's how it is in the standard one. So he's trying to calculate the one for titanium. You get it? So that's the situation there. So because that's going to be 1.22, it means that basically the final electron potential for titanium, yeah, he can basically rearrange the reaction. So E of Ti is going to be equal to E of copper minus E of cell. So because you have E cell is equal to E copper, E titanium, bring that to the other side there and then minus away the E cell. So therefore, E of copper minus E of cell is going to equal E of titanium. So therefore, if you do get this reading, then you're correct and you're going to get 0.88. So that's how it's going to work, yeah? Calm. So that's all you need to write there. Let's move on to part C. Give the half equation for the electrode reaction in the TiO2 plus here, Ti electrode and acidic conditions. So obviously, I need probably some space for this. So obviously, we're going from TiO 2 plus to Ti. So we're going from Ti, that's obviously AQS there, it says it. And we're going to Ti, yeah? So obviously, balance the electrons straight away. We've got 2 plus here. Think about this here. We have an oxidation state of what? This is gonna be 2 plus here. This is 2 minus. And we're trying to make 2 plus. The oxidation state of titanium is gonna be plus 4. So in the future to cancel it out, yeah, we're gonna have to need 4 electrons here. Yeah? We know that from the oxidation state of the metal, yes. That's a quick way if anybody wants to find out how many electrons you're gonna need in the end. You can do it like that. Don't have to though. Yeah, you don't have to. But you can just balance it out normally, and it will work as well. Yeah. So what I mean by this is the next step here would obviously be to balance the oxygens here using H2O. So you got one oxygen on the left hand sside, so you need to add a one H2O on the right hand side. Yeah, that's how you balance ionic equations. And then because you've got two hydrogens now on the right hand side, you need to add two hydrogens to the left. 2H plus to the left. And now you could have balanced it and you'll get 4E minus if you want. If you don't want to balance electrons at the beginning here. And so that's the final equation is 2H plus plus TiO2 plus plus 4E minus gives you Ti plus H2O here. And then obviously add the state symbols. So L, S, is AQ. And then yeah, that's it. H plus is just H plus. Alright, you get that, yeah? So that's C. Alright, calm. Question D, yeah? Give an equation for the reaction between copper and nitric acid here and the explanation. So usually it's explain why copper does not react with most acids but does with nitric acid here. So when they talk about like why it doesn't react or why it does react here, you even need to talk about one is more like oxidizing or one is higher electrical potential, whatever. Or you can also do feasibility shit, yeah. So for copper and nitric acid here, let's see the situation here. Where's copper? Copper is there. Nitric acid is down there, yeah. So obviously this is gonna be going right because it's bigger. That one's gonna be going left because it's smaller. So all you need to do here is just 0.96 minus 0.34. That's gonna give you 0.62, yeah. And obviously that is positive, yeah, which is positive. Therefore, the reaction is feasible. Yeah, remember, if it's positive EMF, then it's a feasible reaction, yeah? So we've got a positive EMF there, so a feasible reaction. And hence, obviously, for the other one, why it doesn't react with the other acid, yeah, like HCl, whatever, wherever this H plus shit has come from, is obviously the copper that's reacting here, it's not gonna, it's gonna react with the acid, bro, yeah? So hence, obviously, the copper is obviously going to be oxidized. It's not going to be reduced here. It's going to be oxidized. Yeah, it's going to give away one of. It's going to still be going left, even though this is bigger than this. It doesn't matter because that's the acid. It's not gonna. It's going to react with the acid. It's going to go left. You understand? The same way it's reacting with nitric acid. It's going to go left here. It's reacting with the acid, so therefore it's going to donate its. Sorry, it's going to. Yeah, donate the E minus here, and it's going to combine with the H plus to produce that. If that makes sense, yeah? So it's going to be E reduced, so the H plus is going to get reduced. So H plus is going to get reduced. So if H plus is going to get reduced here, so you can write here for copper and H plus. So remember, EMF is always so EMF is always, so E cell is always E of reduced minus E of oxidized, yeah? E of reduced is the H plus here, so that's 0. And then minus E of oxidized is 0.34 from the copper. That's going to become negative, so 0.34. So obviously, that's not feasible, yeah, because it's a negative number. So negative, so not feasible, yeah. So that's why it's going to react with the nitric acid, but not any other acid, yeah. Come on. Equation. Come on. So the equation for this here. So you need to combine the top and the bottom equation there. Listen, I'm gonna just do it straight away off the bat. Obviously, you need to find a common factor between these two. So you've got 2 here, you've got 3 here. So I'm gonna need to times the top one by 3 to get 6 electrons, times the bottom one by 2 to get 6 electrons, yeah? So times the bottom one by 2, that's gonna be 2NO 3 plus 8 H plus 6 E minus gets you 2NO plus 4 H2O, yeah? So that's timesing the nitric acid equation by 2, yeah? And then this is going to be going backwards. Remember, this is going forward, that's going backwards because it's smaller. So CO2 plus, Cu2 plus 2E minus here to Cu. So we're going to go other way. So Cu is going to go to Cu2 plus other thing. And we're going to times that by 3. So it's going to be Cu go into E minus plus Cu2 plus. And obviously we need to times that by 3. There was already a 2 here. So therefore, this is going to become 3, this is going to become 3, and it's going to become 6, because of the 2 there in terms of by 3, it's going to become 6. And now it balances nicely, the 6 electrons cancel, and so as a final product, you just got 2NO3 plus 3Cu, so just write the reactants of that and that. And then obviously this is another reactant here, doesn't cancel with anything, so 8H plus, and then that's going to turn into 2NO plus 4H2O. There's no H2Os on the left, so you don't need to worry about uh, cancelling anything out, so 4H2O there. And then obviously we're making also 3Cu2 plus here, so plus 3Cu2 plus here, and that's it. Alright, calm, that's the final equation there, yeah. Question 5, yeah. Alright, calm. That's obviously the salt bridge, yeah. There's enough said there, bro. That's obviously the salt bridge that connects the two, yeah. And the stated purpose of the salt bridge is obviously to complete the circuit. Yeah, because how can you just have like V connected? Like how can you have that battery connected that is not like it's not connected by another wire, you know? Like there's nothing there. It's just imagine that wasn't there. It's just going from that side to that side. There's nothing happening. Alright, calm. And it's not even going from that side to that side because it's voltmeter, so it can't even move. Alright, calm. Name the substance as electrode B in the diagram above. Obviously, you've got a standard electrode bullshit going on the left, which means that obviously that's a different phase. Whenever you've got a different phase or like you've got a gas going into aqueous, that's obviously going to be platinum, yeah? You have to use platinum, yeah? So always just remember that. So obviously this is a platinum electrode, yeah? Calm. Complete table 1 to identify C, D, and E, yeah? So what's C, fam? So C is just the whatever fuck acid has whatever is gonna produce the H plus ions, yeah. So that's in the standard electrode, yeah. So whoever's making this H here, it just needs to be any monoprotic acid, yeah. So just say HCl, yeah. It's calm. I think you can just put H plus as well. And the condition is obviously that the H plus has to be 1 mole per dm cubed in a standard hydrogen electrode, yeah. You can put like H2SO4, like a diprotic one, yeah, but just make sure you put the concentration at 0.5, yeah. So that way 0.5 times 2 is 1, yeah. Alright, D. Let's look at D. D is the gas that's been bubbled in. Obviously, that's hydrogen gas. So that's obviously H2 gas. And obviously, the gas needs to be at 100 kilopascal, yeah. That's the condition. Alright, E. Um, E is the solution that's in there. Obviously, it's ion, so like Fe2 plus, Fe3 plus. That's what we're trying to do here. We're trying to find the potential for Fe3 plus to Fe2 plus. You can write Fe2 plus Fe3 plus, I think, but it's better to just think of a compound, so just FeCl2 and FeCl3. Obviously, that's what's going to make the 2 plus and 3 plus, yeah? Calm. And obviously, the conditions for that is also has to be 1 mole per dm cube, obviously, because hydrogen is. And a proper condition for this as well is 100 kilopascal. You can put that to. Other electrode needs to be, sorry, what the fuck am I talking about? Not 100 kilopascal, it's fucking retarded, that's pressure. I mean, thingy, innit? I mean, 298 Kelvin, yeah? It's Kelvin, yeah? So temperature. The standard electron potential E dash for the Fe whatever is 0.77. Give the ionic equation for the overall reaction in the cell in the diagram above. State the change that needs to be made to the parallelism diagram to show whatever. Okay, cool. So ionic equation, yeah? So obviously Fe is 0.77. So therefore, and the other one is smaller, it's going to be 0. So therefore, this is going to be reduced. Yeah, we're going to go from Fe3 plus to Fe2 plus, yeah? So Fe is going to be, Fe3 plus is going to be reduced here. So therefore, we've got hydrogen here, H2 gas, which is just going to split into 2H plus 2E minus. I don't know if it tells you that, but that's obvious. Yeah, that's the whole point in this situation here. The H2 gas is going to turn into H plus. And obviously to balance H plus, you need the 2E minus here. Come. And now obviously Fe3 plus is going to be reduced, so it's attaching 1 electron to get to Fe2 plus here. Come. So that's going on there. I need to balance the electrons now. I've got 2 electrons down here. I only got 1 there, so balance that. Put 2 there, put 2 there, put 2 there. And now cancel everything, so just write the product. So you just got 2 Fe 3 plus on the left hand side, plus H2 from up here. That's another reactant. That's going to go to 2 Fe 3 plus, by 2 plus here, because that's the product here. And then plus 2H plus here. Go on. That's the ionic equation. What's the change? So to make the cell go to completion here, obviously the change that you need to make here is just by taking out the voltmeter. Obviously voltmeters have very high resistance that allows all the current to go through here, and it basically means that having a voltmeter, the reason it has high resistance, it means it can't affect the reaction here. So therefore no current is going to be moving through V. So to complete this reaction and make it go full way, you obviously just need to remove the voltmeter and put something else there, like a wire or an ammeter or anything there. And obviously that's going to move through that then, and it's going to complete it until both concentrations are the same. So that's all you need to do there. So the right change that you can do is to add, replace voltmeter with a wire here. Or you can say lamp as well. You can say a lot of things here. Alright, cool. The student sets up a cell as shown in the cell representation. The student measures the EMF in the cell with different concentrations at calm. Zn2 over that. So simple. Just do 1 divided by 0.1, that's 10. And then obviously ln of 10 will give you 2.30, yeah? So therefore in here it goes 2.30, yeah? And alright. Then it says to plot all this shit on a graph, so simple, just plot on the graph. I copied and pasted it from the mark scheme. Obviously lnz n2 plus cu2 plus. That's what you're plotting here. So this part here, that's the x-axis, and then the y-axis is there, the e thing here, v. So just plot that correctly. You should get a graph like that. Obviously then draw a straight line of best fit going down. That's the situation here. Alright, come on. G. This equation is in the form of whatever, yeah, in the form y equals mx plus c, yeah. So y is obviously what? Y is E cell, because that's what we plotted on the y-axis here. And on the x-axis, we plotted this whole ln thing here. So that means that x here is this ln shit here. That's the thing that's changing. And plus E cell would therefore be c. So what's m? What's the gradient? The gradient is this thing then. Is this minus 4.3 times 10 to the minus 10 to the 5, yeah? So obviously that means here that I can write m is equal to minus 4.3 times 10 minus 5 t, yeah? Comes. That's the gradient, yeah? Now what you need to do is you need to then find the gradient from the graph so I can find t. You see how it's asking me to find t? It also says find the gradient from the graph, so it gives you a little bit of help there. What you need to do is find gradient of the graph, just take 2 points. I suggest you do it as wide as possible, so take that and take that if you want. and then take that point there, so that's 2 point whatever. I take the y coordinate, and then remember gradient is y2 minus y1 over x2 minus x1, yeah? So just keep them consistent. So take the y2 there, take the x and y coordinate there, take the x and y coordinate up there, do this, do the second y coordinate minus first y coordinate, and second x coordinate minus first x coordinate, you get a gradient. The gradient that you're gonna get apparently is minus 0.013. Yeah, it's gonna be negative obviously because it's going down, yeah, so therefore it's negative gradient, yeah. And so hence what I can say is because 4.3 times 10 minus 5 times t is equal to that, that's equal to the gradient. Just divide by that. So t is equal to minus 0.013 over minus 4.3 times 10 to the power minus 5. And obviously that's going to just be what, fam? 302 apparently, yeah? So 302 Kelvin. And the voltage goes here as well. That is minus 0.013, that's the gradient. Alright, calm. H. An experiment table, whatever, is 0.33. Use data from table 2 and F to calculate the actual potential for Zn experiment 2. So let's just let's just write straight away. Whenever you've got EMFs, always good to write E cell is equal to E reduced minus E oxidized. Yeah. Let's look at the E cell here then. What's the E cell value for experiment 2? It's 1.13. Yeah. So therefore 1.13. What's gonna get reduced and what's gonna get oxidized there? That's what we need to find. So that's gonna be 1.13. And that's going to be equal to that minus that, yeah? So which one's reduced, which one's oxidized? Cu2 to Cu is going to be the reduced one, yeah? That's going to be reduced. Yeah, and the reason you know that's going to be reduced is because you can look back at this equation, this representation, and always the one that's reduced is the one on the right, the one that's oxidized in the left there, yeah? So therefore it's getting reduced, yeah? Cu2 plus turning to Cu, whereas Zn is turning to Zn2 plus, yeah? So therefore it's being reduced, which means that the copper one is a 0.34. That's the one that's going to be reduced. That's 33, not 34, yeah? 33 minus E oxidized. So take that to that side, take away 1.13, and so you're going to get 0.33 minus 1.13, which is going to be minus 0.8 volts, yeah? So that's minus 0.8, so that's electrical potential is minus 0.8, yeah? Alright, come. And then what's the reason that it's different from the standard one? Again, just non-standard conditions here. Just copy and paste answer. Alright, come. Next one. Alright, question 6. Again, bro, E of reduced minus E of oxidized, bro. This is bigger, so this is gonna go forward. That's smaller, so that's going backwards, bro. So that's just gonna be 0.34 minus the smaller one minus 0.44. And so obviously that's gonna produce 0.78, and that's obviously positive, so therefore it's A. Calm. Question 7. Explain how the salt bridge provides an electrical connection. So we can't just say it connects a circuit here. So obviously it's asking how does it connect the circuit here. So you need to say it allows ions to move through it. Yeah, come. The standard electrode potential for Cu2 whatever is 0.34. Yeah. So obviously what's saying here? What's saying? So it's saying calculate electrode potential for the left hand electrode in the diagram. Yeah. The left hand electrode in the diagram is my man there. I should record an initial voltage of 0.16. So obviously, again, E cell, yeah, is equal to E of reduced minus E of oxidized there. So he said that he recorded a voltage of 0.16, so that's E cell, 0.16 here. Now, what's reduced, what's oxidized? He's talking about the left-hand electrode there, yeah? So obviously in the left-hand electrode, that's gonna be the one over there that's gonna be oxidized there. So it's always right minus left here, or reduced minus oxidized here. So it's gonna be oxidized and turn into that. Yes, this one's gonna be oxidized one. So therefore it's gonna be 0.16 is gonna be equal to 0.34, which is the reduced one. So that means that the one that they gave us was reduced, because that's the right-hand one, yeah? So this one's the reduced one. Take away the oxidized, which we don't know. We can just call that X. So bring x to the other side, take away 0.16. Obviously, x is going to be equal to 0.18, which makes sense. Feasible reaction, whatever. 0.18, yeah? Calm. So that's the electric potential there, yeah? Both electrons contain a strip of copper metal in a solution of aqueous Cu2 plus. Yeah, state why the left-hand electrode does not have electric potential of that. Well, obviously, if they're the same solutions, yeah, then that means that the only difference here is that they have to be different concentrations, and that's fucking bait, bro. 0.15, and you got 1. So that's why they're different. Yeah, they have different concentrations, yeah. Alright, calm. The concentration is not 1 mole dm cubed, yeah. Alright, calm. Give a considerable representation for the cell in the diagram. Alright, so you've got a copper electrode, then it's turning into Cu2 plus ions down there, aqueous. Then you're just gonna get a salt bridge here, then Cu2 plus here, and then copper electrode again. Not really much going on, so just write that. So Cu says include state symbols. So Cu solid, change of phase because you're going to aqueous now. So there you go there. 2 plus salt bridge, Cu2 plus, that's aqueous, and then obviously change of phase again to get to the solid electrode potential, which is Cus here. Alright, calm. Solid electrode, yeah, not electrode potential. Alright, calm. Safe. So when a voltmeter is replaced by a bulb, that's what we're talking about earlier, completing the circuit. Yeah, give one reason why the EMF of the thing decreases to 0. So the EMF will go to 0 because the reaction is going to end at some point. It's going to end the reaction. The reason for that is the change in concentration of copper ions on left-hand electrodes. Obviously, you've got 0.1 here, you've got 1 there. So therefore the copper electrode here is going to increase in concentration to match the one on the right hand side. If I replace that with a wire, it's going to go like that. It's going to increase in concentration, so it's going to get to 1. And then when it gets to 1, the whole concentration is going to stop because there's no difference between them now. They're going to have the same electro potential. Yeah. So hence, that's why I need to write. The one on the left hand side is increasing. And then the reason why the AMF will go to 0 is the concentration. The concentration of the Cu2 plus ions in both solutions will become equal, yeah? So that's the reason right there. I'm trying to make that mistake no more time. I'm just gonna leave that. Alright, calm. Question 8. Which ion cannot catalyze the reaction between iodide and whatever? Yeah? So which reaction cannot do that? Well, bruv, like, it's kind of bait. I'm not even gonna lie. We've got iodide and myoman. So we've got iodide here. So which ones cannot catalyze that? The reason why is because we've got this and this thing here. So reason why it's asking which one is not going to do that is obviously got a negative ion reacting with a negative ion, which is going to be bare slow. So you're going to need to have a obviously this is going to be forward reactions bigger. It's going to be negative reactions smaller. So that therefore you need a catalyst here. Listen, the catalyst should be between them. Should have electric potential between these two. Yeah. So it should be either this or this. So which one that's not going to be? It's going to be this Cr2 plus here. So that's not going to work here. Reason being is obviously it has a smaller electric potential than iodide. So yeah, man, it ain't gonna work. It's gonna react to what you want basically is it to have a smaller one than S2O8 minus, so it can react with the SO2 minus to create SO4 plus, basically help it out in a way, and then react with iodide. This one's smaller, so it's even gonna react with iodide anyway. It's not even gonna react with the S2O8, yeah. So therefore, it's just Cr2 plus here, and it's kind of big because it's the only one that's on its own down there, yeah. So the catalyst should be between them. Yeah. Alright, calm. It's a bit of a fugazi explanation, but you get the gist in it. Alright, question 9. Use the table to deduce a species that is the best oxidizing agent. Yeah, so obviously here we got they're all being reduced. So if something is reduced, yeah, if something is an oxidizing agent, yeah, that means that it's being reduced itself. Yeah. So which thing here is the best at being reduced? All of the ones on the left hand side are getting reduced to the right hand side. This one has the most powerful electron potential, 1.36. So that means that CO2 is getting reduced pairs. So therefore it's the best oxidizing agent. So CO2. Cool. B. Write down the conventional representation for a cell used to measure the standard electrical potential for the conversion of tin ions to tin. So obviously, if it's standard electron, you got H on the left hand side. So you got PT, always platinum because you've got H2 gas that's coming in. Got H2 gas coming in, it's changing phase to H plus aqueous ions. Then we've got the salt bridge down on the right hand side. You just got the oxidized turning into the whatever. You get me? So the oxidized turning into the reduced. That's Sm plus. That's the thing that's telling us 2 plus here because 2 plus ions. It says it there. And then dash another phase change in Sn because you're going from aqueous to solid here, and that's the electrode over there. So there you go. Save. A cell was made by converting two half cells of a salt bridge, one whatever. Calculate the EMF of the cell, write a half equation. Okay, cool. Which one is it? One half cell connected of silver nitrate. The other one is tin nitrate. So we've got silver and tin. So this one and this one. So obviously silver and tin. Which one's bigger? 0.8 is bigger. 0.14 is smaller. So this is going to be going forward. That's going to be going backward. So we're going to do 0.8 minus 0.14, yeah? So therefore it's just the EMF is just 0.8 minus 0.14, or the reduced minus oxidized. That's going to be 0.94. Yeah, and it says half equation. Well, tin is just being oxidized, yeah. So it's just going from Sn to Sn2 plus 2E minus. Yeah, it knows being oxidized because small electric potential, yeah. So that's it there. And it's reduced minus oxidized, yeah. Alright, calm. Use data from the table above to write an equation for the reaction of silver with iron, yeah. Okay, so same thing here. Should look at Fe2 then. Fe is smaller than Ag. So Ag is going to be going forward. Fe is going to be going backward. Did I? Well, you read it again. Oh no, silver with iron ions, yeah? So if it's silver with iron ions here, then that means it's gonna be, we're looking at this shit here. Fe3 plus the Fe2 plus this, so forget about what I said down here. So this one's gonna be going backwards because it's smaller than Ag, just smaller 0.77. So that's going backwards, that's going forward. So it's gonna be Fe2 plus Ag plus. It's gonna go to Ag and Fe3 plus. Electrons is one electron there, one electron there, so it's gonna balance anyway, yeah? So there you go. It's very simple, yeah. Just Fe2 plus Ag plus gonna go to Ag, and then my man's gonna get oxidized 3 plus. Alright, calm. Is that meant to be a plus sign? Why is my writing so dead? Alright, question 10. I think it's the last step in my life. Yeah, something like that. This and 11, and 11 is multiple trace. Alright, calm. So fuel cell, whatever, calm. Let's just skip to the actual question. A salt bridge was used in a cell to measure electrical potential. Explain the function of a salt bridge. It completes the circuit. And there's two marks here, so you need to say by, it says explain the function, not just what is the function here. So by allowing the ions, so that the K to flow, yeah, or to move, yeah. So obviously you got like KNO3 or whatever inside the salt bridge. Those are the ions that are in there, positive and negative ions. They're going to be moving around. That's what's going to carry the charge or whatever. Alright, calm. Use data up on the table above to deduce the weakest down. The weakest here. So the weakest reducing agent means that it's going to be, so all of these ones on the left are reducing. Weakest reducing agent means it needs to be oxidized there. So we're looking at things on the right here. So obviously F2 goes that way very strongly. That's the highest one, plus 2.8. So it's very good at reducing. So therefore F minus is rare that it's going to go back. It's rare that it can oxidize here because it has such a strong one going that way. So therefore the halide that's going to be the weakest reducing agent is F minus here. Use data from the table to justify why sulfate solution cannot be capable of oxidizing. So similar thing with electron potentials. Let's look at sulfate. Sulfate is down here 0.17, and bromide is what, 1.07. So obviously the sulfate electric potential of sulfate ion is obviously less than the electric potential of bromide. Yeah, that's all you need to write. So why would it oxidize it? You know what I mean? And we just said that our oxidizing agent is the worst up here, right? As you go above. You get what I'm saying? So why would that oxidize it when that can be reduced and that can be, yeah, calm. Come. Use data from table to calculate a value for EMF of a hydrogen oxide thing, yeah? By the way, what I mean by this is it should not be capable of oxidizing, so it itself is going to be reduced. BR2 has a higher reducing power because 1.07 is bigger than 0.17, so it has a higher reducing power. So therefore, why would it be reduced by my man, you know? That's the whole point. I mean, oxidized by my man. You see what I'm trying to say? But then the other one's gonna itself get reduced. Do you see what I mean? Yeah? I don't know if that makes sense, but yeah. If you get what I mean, then you get what I mean, innit? But I'm saying that like it's like the F minus here is a very weak reducing agent here, but this is the opposite way. So here, the more you go down, it's gonna be the stronger one, yeah? You get what I'm saying? That probably made no sense. Listen, BR2, yeah, it goes to that. It has a strong reduction there, yeah? And so why would it oxidize that backwards, yeah, if it has a stronger reduction going forward compared to the reduction of my man here, SO? You get what I'm saying? Go on. Use data from the table to calculate the value for the EMF of a hydrogen cell operate under alkali conditions. So hydrogen cell is simple. It's just gonna be, you need to remember the half equations for hydrogen cell is this one over here. Obviously, what is it? What is it? Calculate the value, yeah? So that's the value there. But we need to obviously split that up into how to make that. So obviously it's this one here and this one here. Yes, these are the two half equations for hydrogen. So yeah, as you see when you combine them, it's gonna combine to make that one there for the 1.23. So it's just gonna be bigger one minus smaller one, bigger one is 0.4, smaller one is minus 0.83. So 0.4 minus 0.83, that's gonna be 1.23 volts here. Uh, um, question E, yeah. There are two ways to use hydrogen as a fuel for cars here. One is in a fuel cell to power electric motor, the other is in a fuel cell and internal combustion engine here. So obviously combustion engine is going to be releasing bare heat. So it's just going to convert more energy from the combustion of the hydrogen into kinetic energy and it's going to release less heat here. The following cell has an EMF of 0.46. Which statement above the operation of the cell is obviously reduce, oxidize, oxidize, reduce. So reduce, oxidize, oxidize, reduce. So obviously copper is being oxidized, going from reduced state to oxidized state by the Ag, and the Ag is being reduced, going from oxidized to reduced. So obviously it's part A. It's not even a question. There you go. Anyway, man, that's it. It's been life hacks, man.